we are now going to start topology from Munkres' book. Now, the first chapter is about preliminaries, which are basically the same things that you see in other books at this level. Sets, functions, those things. Cartesian product equivalence relation. So there is no point repeating those things here again because we have already gone through most of them in Terence-Tau's analysis. There is, however, one thing from that book that I skipped, namely order relations. Now we are going to need this thing, this notion, because we will have some examples of topological spaces which involve this type of relations, and they are going to be very important examples. So let's start with this notion instead of starting again from sets. And for that, let's just go back to the notion of relations itself, and which just simply for us that means binary relations. Let's start with this example. Consider the set consisting of these three integers 0, -1 and 2. Now you already know from number theory that we have the notion of divisibility, one integer dividing another integer, and we denote that by using this notation. This means that a and b are integers and a divides b, or b is divisible by a, and you already know what this means. For example, 2 divides 4. 4 does not divide 2. Okay, so if we now imagine this relation but on the elements of this set, then what are the pairs of integers we are going to get? 0 doesn't divide anything, so 0 cannot be the first element of this relation. What about -1? -1 divides everything, just like 1. Everything means every integer. So -1 divides 0, -1 divides -1, and -1 divides 2. What about 2? 2 divides 0. 0 doesn't divide anything, including itself, but any non-zero integer divides 0. 2 doesn't divide -1, but 2 divides itself. Okay. Now, if we use a different notation to express the fact that 2 divides 4, what different notation? Say I use an ordered pair. And by this ordered pair, I will understand that, okay, 2 divides 4. Absence of 4, 2 means that 4 does not divide 2. If I use ordered pairs in this sense, then these relations are going to look like this. These relations means, of course, that this is only one relation, but these instances of that relation. Now, if we consider the collection of these things and even give it a name, say C, what do you notice about this C? You notice that its elements are ordered pairs. Ordered pairs of what? Ordered pairs of objects which are elements of A. And that's why this is a subset of the Cartesian product A times A. Notice carefully that this set of ordered pairs fully expresses this divisibility relation when only elements of A are involved. That means instead of saying that we are considering the divisibility relation on A, we can also say the set C. The set C itself tells us fully what this relation is, which elements are related to which elements and which elements are not related to which elements. In that sense, for example, we do not see 0 comma something because 0 is not related to anything in that way by this relation. However, 2 is related to 0. So there is an asymmetry in this relation. 0 is not related to 2, but 2 is related to 0. That's not the main point here. The point here is that we can use sets of ordered pairs to express any type of relation fully. Binary relations, of course, relations relating two objects of a set. And this gives us an idea of the general definition. And you already know this definition. So the definition is just this: let A be a set, any subset C of the Cartesian product A times A is called a relation on A, on the set A. For example, this is a relation on the set A. This is the divisibility relation on the set A. Okay, so this is nothing new to us, but now we are going to see the notion of ordered relations. And this is found in the third section of the first chapter. So the third section we are going to see, but from this point, not fully. I mean, before the notion of ordered relations, you have equivalence relations, those things, we already know about them. Ordered relation. Let A be a set and C be a relation on A. Now that I am going to define ordered relations, I remember something. I should have actually said it here itself. Instead, it will be, in fact, easier to understand if we go back to the example. Do you see this statement -1, 0 belongs to C? Of course, you know what it means. But in the context of our relations, what this means is that -1 is related to 0. Or if we actually go back to what the relation really is, -1 divides 0. Instead of using this cumbersome way to express that statement, we can also simplify things by writing like this: -1 C0. This also is supposed to mean that same thing. It's that same piece of information but written slightly differently and using less symbols. Or how do you read this? -1 C0. If you want to be more expressive, you can say -1 is C related to 0. This means that -1 is related to 0 by the relation C. Okay? And usually we do not use letters. Letters, of course, are used to denote sets, and relations by definition are sets after all. But still, we normally use some kind of symbol. Say that symbol is star. Then we would write like this: this will also mean that minus 1 divides 0. In fact, we have a symbol here, that vertical bar. Okay, so this and this all mean the same thing, that minus 1 divides 0. Okay, now we can define order relation, but we are going to use this notation. Then it will be easier to write. We all see an order relation or simple order. It has other names also. Or linear order if the following are satisfied. Just like the notion of equivalence relations uses 3 conditions: reflexivity, symmetry and transitivity in its definition. Here also we have 3 conditions, but the conditions are different. Transitivity is still there. The first one is called comparability for any two elements x and y, distinct elements actually. If x is not equal to y, then either x is related to y by c or y is related to x by c. This is called comparability because what this is saying basically is that if you choose distinct elements from A, then they are comparable by the relation in one of the 2 ways. Either this is true or this is true. Or maybe both are also true, who knows, because in mathematics usually OR is inclusive OR. So OR means something is true or something else is true, or both are true. Okay, that condition is included. So this is comparability. The second condition is non-reflexivity. This is the exact opposite of reflexivity. For any x in A, x is not C related to x. This means that the ordered pair x comma x is not in the set C, and this should be true for every x in A. I say exact opposite to reflexivity because in reflexivity all those pairs x comma x have to be in the relation. Here none of them can be in the relation. That is non-reflexivity. And finally, the third one you already know. Transitivity for any 3 elements x, y and z, not necessarily distinct. If x is related to y and y is related to z, then x is related to z. If these 3 conditions are satisfied by the relation C, then we call it an ordered relation on A, or a simple order or a linear order. And when you have a set A, with an ordered relation on it, then this pair where you have the set and the relation is called an ordered set. An ordered set is not merely a set but a set on which an ordered relation has been defined. Now let's see two remarks about this definition. One of the remarks is just about the name, ordered relation. What we are calling ordered relations, some other mathematicians would give a different name to these relations. Usually these relations are called strict linear order relation. That's the more common name given to this type of relations. But for some reason, the author has chosen to call these relations itself in this book ordered relations. So that's one thing. And the other thing is a consequence of these conditions. Say you have an ordered set A with an ordered relation C on A. Now what does the comparability condition say? That if you choose distinct elements x and y in A, then either x is related to y or y is related to x. And I said moments ago that both of them may also be true simultaneously. Let's see what happens if both of them are true. Suppose we have this. For distinct elements x and y. X is related to y and y is related to x. Now look at transitivity. What does transitivity say then? Obviously, then x is related to x. Think of transitivity with x in place of z. That can be true, right? You can consider x, y and x. But then this goes against non-reflexivity. So that is why this cannot be true. Although here we don't really know whether they can simultaneously be true. But now combining these three conditions, we see that no, something goes wrong. So actually they cannot be true. When you consider two distinct elements, exactly one of these things has to be true and the other will be false. Okay. So that's our linear order, or more accurately or more commonly known as strict linear order. Now, I already said while discussing that first example that we don't normally use letters here. Instead, we use symbols. Now, this is a symbol that is normally used to denote a generic equivalence relation. When we talk about equivalence relations, this is the symbol that we normally use. It's like a group operation. If you use the multiplicative notation in writing a group, you don't write anything for the binary operation. But occasionally, you write things like this. G comma star is a group, where star denotes a binary operation. We don't really know what it is. Maybe G is an abstract group, something. So we write star. Just like that, we use this symbol to denote a general equivalence relation. Just like that, there is also a symbol for denoting an ordered relation, or the type of ordered relation we are considering here, strict linear order. And that symbol is your usual less than symbol. Now, if you express these conditions using this symbol, they won't change, of course, but their appearance will change. So let's see how they look with this. You just have to change the things here. See how natural they look now and how much more easy to understand now they have become when we use this symbol. It says that if we consider two distinct elements of A, then X is again, because we are using this symbol doesn't mean we get to read it like this, X is less than Y. This is no longer less than, this is just a symbol which reminds us of the usual less than, because its properties are like the usual less than, which applies to numbers. But in this form, it's easier to understand and remember. Either X is related to Y or Y is related to X. And there is immediately a sense that both of them should not be simultaneously true, which we saw is actually the case. Also, no element is related to itself, and of course, transitivity has its own meaning. Now, let's see two examples. The first example is in the book, it's example 7. That's because we have started somewhere in the middle of the third section. No, we have skipped the part which discusses equivalence relations, those things. So there you have example 1. The usual order relation, or I cannot use the term order relation now itself. The usual relation less than on the set of real numbers is an order relation. And the conditions here follow from the properties of real numbers. In fact, in Terence-Tau's analysis, we rigorously proved these things. We defined this usual order relation on R, and we proved these properties. For example, if we are given two distinct real numbers, x and y, then either x is less than y or y is less than x. Now, this is really less than, the less than that we know. Also, no real number is less than itself. And transitivity, of course, it has that meaning. Okay, so clearly this is an order relation. And in fact, this example is the source of this notation. And this idea also, the general idea, this is the source of that idea. Next, let's see example 8. Now, in example 8, we are going to consider three relations which already have been discussed earlier in the book, but because we haven't seen them, so we'll have to write them here. These are human relations which relate to two persons. Let T be the set of all people in the world this is where it stops, the sentence stops in the book, but let's be more clear. Who have ever been born. That means the people who are alive today, like you and me, and also those people who passed away. All of them combined, that's the set P. Consider the following relations on P. Do not erroneously write on P times P, okay, that will have a different meaning. On P itself means that the relation will be a subset of P times P. First we have D. It's the set of all ordered pairs of human beings such that X is a descendant of Y. Accordingly, this relation is being given the name D, descendant relation. Then we have B, blood relation. P times P such that X and Y have a common ancestor. Okay, X and Y are related by blood. If you look at the family tree of X and Y, there is some common ancestor from whom they have come. And the descendant relation, of course, X has come from Y. If you look at the family tree of X and look at the higher levels, that is people who came before X came, there somewhere Y is sitting as a node. And finally, you have S, the sibling relation. X and Y have the same parents. That is, they are siblings, brother, sister, brother, that type of thing. Now, which one of these is or are ordered relations and which ones are not? Let's see that. What about the descendant relation? Because that we have written first. Actually, let's talk about the blood relation first, because it's the worst. Not because it's blood, but it doesn't satisfy any of the three conditions that we have in the definition of an ordered relation. How so? Let's see the conditions one by one. The first condition is comparability, which says that if you choose any two elements which are distinct, here this means choosing two persons who are not the same, some two persons, okay. X and Y have a common ancestor. That's not necessary. The family trees of X and Y may not have anything common. Say, I am here, I am an Indian, you may be from somewhere else very far away, and there is nothing common between our family trees. Then, in spite of being distinct persons, we are not related by this relation. X is not by, xby is not true, ybx is also not true. And in fact, in this case, you can see that the relation is symmetric. If X and Y have a common ancestor, then Y and X also have a common ancestor. So it's not necessary that any two distinct persons must have a common ancestor, and that is why this relation doesn't satisfy comparability. Does it satisfy non-reflexivity? Of course not. In fact, this is reflexive. X and X have a common ancestor. You and you have a common ancestor. For example, your father or your mother or your grandfather. Although it sounds silly, but technically you and you are related. You are related to itself by this relation, blood. What about transitivity? Transitivity may not immediately be apparent, but this is how you can see that it's not transitive. Say, we have a male and a female, or let me just put a note here, say this is the son, this is the father, and this is the mother. The son has come from his father and mother, but the father and mother themselves, they came from someone else. In relation to the son, say grandpa from father's side. And grandpa from mother's side. So, father is, let me call the father F, the son S, and the mother M. F, B, S. Why? Because father and son have a common ancestor, grandpa. Also, S, B, M. Son and mother also have a common ancestor, grandpa from the mother's side, maternal grandfather. However, F and M are not related by blood. It better not be, okay? So you can see that in spite of having these two relations, this is not true, and that is why this is not transitive either. It is the worst in terms of ordered relation. Then if you look at the sibling relation, the sibling relation only satisfies transitivity. If you have two persons, say S1 and S2, if they are siblings, then they have the same father and same mother. If S2 and S3 are also siblings, they also have the same father and same mother. So automatically S1 and S3 will have that same father and same mother, and so will also be siblings. So this is transitive. However, this is not comparable. And this is also not non-reflexive. Absence of non-reflexivity can be seen immediately because it's about, say, you and you. You are your own sibling. It sounds stupid, but technically it is true. I mean, in this context, it is true. You are your own sibling, so obviously non-reflexivity is not true. Similarly, comparability is also not true. Why? Because do not forget that we are not talking about people from the same family. We are talking about all the people in the world. So if you arbitrarily choose two persons who are not the same person, then they may not be siblings. And in fact, if you just choose someone from your house and someone from a neighboring house, you are not siblings, okay? I hope you are not. So that is why the S relation, although it satisfies transitivity, but it doesn't satisfy comparability or reflexivity. And what about the descendant relation? The descendant relation doesn't satisfy comparability. Again, for the same reason, if you just arbitrarily choose two persons from the population, or maybe someone who passed away and someone who is alive now, it's not necessary that one of them is the descendant of the other. That's not necessary, obviously. So comparability is not present here. What about non-reflexivity, non-reflexivity is present here because you are not a descendant of yourself. Obviously, you cannot give birth to yourself, or you cannot actually have come from yourself. I hope that never happens. So it is satisfying non-reflexivity, and transitivity is easy. Now, say you have a person X who is a descendant of Y. So, in the family tree of X, Y sits somewhere at a higher level or older level than where X is, and Y is related to some other person. So, Y himself or herself may have come from some other person Z, then obviously X itself came from Z, and that's why X is also related to Z. So D satisfies 2 and 3, but it doesn't satisfy 1. Now there is a name to those relations which satisfy 2 and 3, not saying anything about 1. They are called strict partial order relations. Comparability may be absent, may be present. We will consider these strict partial order relations at some point in this book. So let me just end here itself today. There are many more things here, so slowly we will see what they mean and how they are ultimately going to help us in creating some examples of topological spaces. These will be important examples because these spaces will have one property but not the other. So we will see all these things. So that's just it for tonight. Tomorrow also we have an upload, but it's not about these usual things. So see you tomorrow with that, whatever it will be. So until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.